everyone. In this video, we will be studying about the virtual memory management. So, before going to study what is virtual memory, first let us know what is the motivation. Why do we need this virtual memory? So, let us take an example that whenever you are executing a program, first that program or that application should be brought into the main memory. Then only we can start this execution. And suppose now if there is a shortage of memory and the size of that process completely cannot fit into that memory space available, then we cannot load the process completely. So since we cannot load the process completely into the memory, then we cannot execute that process. So our problem here is, even if small amount of space is available, what is required for time being, that part of the process can be brought into the memory and start execution. So, but this does not happen traditionally. So, for that purpose, we are going for this virtual memory. So, in this virtual memory, it is possible to load only a part of a process into the memory and start the execution. When the other part is required of that process, we can bring that other part when only it is required by the processor. At that time only we can bring that part of the process into the memory. So this is called as virtual memory. So let us see, there are many examples where we do not require the complete application or the complete process to be loaded into the main memory. Let us take example now. The size of the process may be large because of the declaration of some variables. Example, when we are declaring an array, we always declare the array size which is bigger than that is required. For example, if we are declaring array of 100 by 100, means what? 100 rows, 100 columns. So how much it will be requiring space for 100 rows and 100 columns? So that is into the size of that particular data type. But out of those 100 by 100 memory spaces, we are only just using 10 by 10. That is 10 rows and 10 columns. Remaining 90 rows and 90 columns, the space required for that is wasted. Is it not? That is not required. So this makes, such type of declaration makes the memory space of that particular process bigger, and we cannot load that process completely into the memory. Another thing is, see, when you are executing some programs and you are checking for the if condition there. If the condition is always true, then we are executing only the if part. That time, no need of bringing the else part into the program. It is not at all executed even once. Then why to bring that part of the program into the memory? Is it not? So, in such cases also, complete program need not be loaded into the memory. Then another example, let us take that. Suppose when we are thinking that some part of the code of the memory produces the error. So when it is producing an error, we are putting that part of code into the try and catch block. See, if the error occurs, then only the catch block will be executed. Of course, we have to write a catch block for every try block. But if the error is executed, if error is occurring, then only the catch block will be executed. Otherwise, it will not be executed. So, there is no need of bringing the catch block until and unless it is required. So, these are few examples which tell that only a part of the program or a application can be loaded into the memory and start its execution. So, this is known as the virtual memory concept. Virtual memory allows you the execution of the process even if the complete program is not in the memory. So, due to this, what are the benefits we are going to get here? So, first of all, the program is not concerned with the physical size of the memory here. Is it not? A programmer would not think about what should be the size of this program so that it can be fitted into the memory. So, this constraint is ruled out. Next, many programs can run at the same time. Why many programs can run? Since only a part of that program is to be brought into the memory, less amount of memory consumption takes place. So, many programs can run at the same time, which will increase the CPU utilization and the throughput. Throughput means the efficiency, that is execution of the processes per unit of time, that will be increased. Then we will be requiring the less I/O, which is input output operation, to load and swap the user programs into the memory. So these are the different benefits which we are going to get. Of course, there are many others, but often these are considerable benefits of the virtual memory. So here in the diagram you can see here, so the area between the stack and the heap, this is the virtual memory here. So the heap means whatever dynamically we are going to allocate the memory, that will be stored in this heap. Heap will grow upwards and the stack will grow downwards. So the area in between this stack and heap is given for the virtual memory. Then apart from allowing you to execute the programs, what you can say, partially when it is brought into the memory, so this virtual memory also gives the another special character of sharing the pages here. Suppose when you want to share the page, see when you are doing a fork system call, that time you want to, the child process will be using the whatever data is present within the parent, that will be used, means duplication will be done. But to avoid this, we can just share those. Okay, we can share those pages. Now you can see here, these are the two processes, process 1 and 2. Between these, their library is being shared here. So what are the pages of these libraries? They can be shared using this virtual memory concept here. During the creation of the fork only, this sharing of pages can take place. So having understood these basic concepts about the virtual memory and benefits and its sharing, next we are going for the demand paging. So as the name itself will indicate, demand paging. Paging means what? We are assuming that the logical memory is divided in terms of pages and the physical memory in terms of frames here. So demand paging means what? So whenever there is a demand, for those for the particular pages, only that time the pages will be brought into the memory. So that is called as demand paging. So when you are doing this demand paging, if the space is available, then that space can be utilized, and if it is not available, then we can swap out which are not used pages and swap in the new pages which are demanded here. So whenever a process or a program wants to be executed, so two options we are having of loading that program into the memory. That is, load the complete program, entire complete program into the memory. Even if some part of that the program is not required, still we are loading the complete part of that program into the memory. Another option is to load only a small part of the process which is just required at the current moment here. So this diagram will depict whatever we have understood till now here. So program A was currently executing, but at that moment program B was demanded by the processor. Then what will happen? The operating system, what it will do, or the swapper, what it will do? It will swap out the pages of program A to the backing store. What is backing store? Backing store is a fast access disk from which the data will be taken into the main memory. So that is the backing store. So the pages of this program A will be swapped out and new pages required for program B will be brought into the memory here. Please remember only those pages which we are required for now. Then how to understand which pages will be required for the execution of that program B. Here the swapper or the pager will assume or will predict few number of pages that may be used by that program B, and it will take only those pages into the memory. It is just a prediction here. So if those pages are not required, again they will be swapped out and the required demanded pages will be brought in. On demand, everything swapping happens here. So in this, normal swapper is not used, or lazy swapper is used. What do you mean by lazy swapper? This swapper will be idle until there is a request for swapping. Only whenever those pages are required, only at that time that lazy swapper will be active and it will swap out the old pages and bring in the new pages to the memory. So this is done by a lazy swapper. So then when you are doing this swapping, see for example now page number 4, 5, 6 and 7, they were previously present into the memory, but after some time when program B started executing, these program A pages have gone out of this memory and they are present in backing store. So where the details of these pages will be present in the page table. So the page table details should be updated that these pages are not present into the memory, only the pages of program B are present. How do we do this? For doing this, we are using an extra bit called as a valid and invalid bit. So only those pages which are present into the main memory, those pages will be marked as valid, and other pages which are not present, those will be marked as invalid. Now see here in this example diagram of the logical memory, we are having 6 pages from 0 to 5 which are containing A to F here. But in the physical memory on the right side, you can see that there are only 3 pages in the physical memory. So the physical memory starts from where? Physical memory is having only A, C and F here. So only these 3 pages. A is which page number? A is page number 0. C is page number 2 and F is page number 5. So page number 0, 2 and 5 should be marked as valid and other pages should be marked as invalid. So here it is frame number 4 and it is marked as valid. Here it is frame number 6 valid, frame number 9 valid. So you can see the entries of all other pages here 1, 3, 4, 6 and 7, they are marked as invalid. What do they state? They state that these pages are not present into the physical memory. So by doing this, we can the operating system or the swapper can understand which pages are present into the memory and which are not present into the memory here. So like this, the validity of the frames is being checked here. Now next concept is, see, whenever a page will be referenced by a processor, okay, so whenever page will be referenced by a process, if that page is present in the memory, then its corresponding entry will be present in the page table, is it not? So if it is present in the main memory, then its entry will be present into the page table. So if it is not present, if any of the page which is referenced by the processor here, if it is not present in the physical memory, then its data also will be not present in the page table. Such situation is called as a page fault. What is a page fault? Suppose if the page referenced does not exist in the memory, its bit is marked as invalid and in the page table, and this is called as a page fault. Then what to do? What should be done when there page fault occurs? So when a page fault occurs, what you have to do? See here, this diagram, whatever explanation I have written here, I will explain using this diagram here. Suppose a processor is referencing this page M, but this page M is not present in the page table. Its page is marked as invalid. Means what it will do now? It will generate a trap and it will generate a interrupt actually. Interrupt is nothing but here in terms of trap. So it will generate a trap to the operating system saying that this particular page is not present in the memory. Then next, a control is handed over to operating system. Then what operating system will do? It will first check whether the page which is referenced is belonging to that process or not. So first it is going to check the validity of the page reference. If that page is not belonging to that process but still it is referenced, then the process will be immediately terminated. Okay, it will be terminated because it is illegal reference to some page. Then suppose if it is legal, means the page which is referenced now, if it is belonging to that process only, then what operating system will do? It will schedule a disk read. It will schedule a disk read from the backing store. It will locate that page which is required. After locating that page will be loaded into the memory wherever the free frame is present. So once it is loaded into the memory, its entry should be made in the page table. Page table updation happens. So after the updation of page table, again that particular instruction is restarted. So these are the steps to be followed when the page fault occurs. So first step, when a page fault occurs, the control is handed over to operating system, giving a trap here. Operating system then checks for the legality of that reference. If it is legal reference, then it is scheduling a disk read, reading that particular page in a free frame in the memory, updating the page table, and restarting that instruction again. So this is the mechanism when a page fault occurs. We have to follow these page fault mechanisms. Then what is the hardware support which is required for this page fault mechanism? Is just a page table you have to require and a backing store or the secondary disk from which the data will be taken and loaded into the memory. These two are already present with us. We have studied in the paging techniques. So next concept we will be studying about the copy on write. So we know that whenever a fork system call is executed, what happens? A child process is created. So when a child process is created, it has the ability to duplicate the same address space of the parent. What threads are present in the parent, all those will be duplicated in the thread process. So after duplicating this one, the child process will execute this exec system call. So when this exec system call will be executed, whatever parent's address space will be there, that will be replaced by the child address space. So there is no meaning in copying the parent's address space at the beginning, is it not? So when a fork system call happens, what we are going to do? The child process will copy its own parent's address space, and suddenly child will execute the execute system call, where it will delete all this address space, means all the threads of the parent, and establish its own address space. So there is no use of copying the parent's address space here. So to avoid this situation, what we are going to do is copy on write concept we are going to use here. So what is this copy on write? So process 1 is a parent process, and it will execute a fork system call which will give birth to the child process, that is process P2. So parent 1, process 1 is having 3 pages with it, that is page A, B and C here. So instead of having the duplicate pages also present in this child process, what we are going to do is we are going to share these pages among the parent and the child. Share means what? We are not going to duplicate. Only one copy, original copy of that page A, B and C is kept, and then we are going to share them. Suppose now if any one of the process wants to modify the data in any of these pages. Suppose if any one of these processes, process P1 or process P2, if any one of the processes wants to modify the data of this A, B and C, what will happen now? A copy of those pages will be created and placed in some of the free frame. A copy of those pages. Suppose here process P2 is wanting to modify this page C here. So directly it cannot modify the original page, whereas copy of that page will be kept here. Okay, copy of that page will be kept, and that copy page can be modified. Original copies will be kept as it is. If any of the process, be it a parent or be it a child, if any of the processes wants to modify these pages, a copy is created. And please remember that a copy is created only when we want to modify. If you do not want to modify, just use the data in those pages, then copy of that page is not created. Only a copy is created when you are going to modify. So using this concept, this copying or duplicating the parent space by the child space will be avoided. So this is the Copyonwrite concept. Next we are going to see what happens when there is a page fault. We have already seen. And then when there is a page fault, what are the different steps here? See, when a page fault occurs, the page which is not in the memory should be brought into the disk. Then if the disk frame is free, then we are going to use that frame for bringing the new page into that frame. Suppose if that frame is not free, so if there are no frames here, if there is no free frame, what we are going to do is we are going to use any one of the page replacement algorithm. Means in this page replacement algorithm, a victim page is selected, a victim frame, a target frame is selected, and that target will be swapped out of the disk. Swapped out of the memory, and it will be copied to the disk, and the new page is brought in that free frame. So this is followed here. So after that, what we are going to do? We are bringing in the new page into that free frame, and we are going to restart the process here. So what we have to remember here, when there is no free frame, we are going to swap out one of the frame's content, means one of the frame is going to be returned back into the disk here. Here also one more concept we have to study, that is, whenever you are choosing a victim here, it should be returned back into the disk, so that it will become free and a new page is brought into it. Then every time copying the data of this victim frame into the backing store, is it necessary? Let us see now. Suppose that one page is brought into this frame, and when it is brought till it is swapped out, no modifications are done. Okay, only the data is read here. No modification is done. When you have not done any modification, then it will be having the same contents as that present in the backing store. Is it not? Then again, why to copy the same data while swapping out? We don't want to copy. So if and only if modification is done to that victim page, then only it should be copied back into the backing store. Otherwise, simply we can discard. Is it not? So to establish this mechanism, we are using a bit called as a modify bit or a dirty bit. So what is this modify bit or a dirty bit is, whenever a page is brought into a physical memory, that page is having a extra bit called as modify bit or a dirty bit. So if that bit is set to 1, it means that that particular page is being modified. That particular page is modified, and while you are swapping out that page, we have to copy it back to the backing store. So this is the process which is to be followed. Suppose if the modify or the dirty bit is not set, means it is 0, then simply we can discard that victim, because a copy of that is already present in the backing store. No need to again copy the same thing into the backing store. So by using this modify bit, we are reducing the copy mechanism here. So this diagram will tell you how the when the page fault occurs, and how you are going to manage these modified bits. So first what we are going to do is, if there are no free frames, then what we are going to do, we are going to select one victim using any one page replacement algorithm. So after selecting that one, we are writing this victim back to the backing store if its modified bit is set to 1, or we are just discarding that data if its modified bit is set to 0 here. Then after swapping out, next what we are going, see, when this frame is not present into the physical memory, its page table should be updated saying that this frame is invalid now. So we are going to update. So after updating, the new page which is required, that is brought and stored in this free frame now. After storing, again we are updating that this particular frame number F is a valid frame and it is present in the physical memory here. So we are updating. After updating, what we are doing? Restart the instruction whatever we are had before for this page which is brought into the main memory now. So these are the steps followed. So for using the when a page fault occurs, this is the extended version of the mechanism here. So whenever a page fault occurs, what we are going to do is we are going to select a victim using any one of the page replacement algorithm. Then if it is modified bit is set to 1, then we are going to copy it into the backing store. Otherwise, just discard this one and make a free frame here. After making a free frame, update the page table, that is invalid and valid bit is to be set here. New page is brought into the free frame. Then again the page table is set and restart is done. So this is the method which is to be followed when a page fault occurs for swapping. So now we have seen here for choosing a victim, we are going to select many page replacement algorithm. We have to select a victim using any page replacement. So next we'll be studying about the page replacement algorithms in the next video. Thank you.